Hello, my name is Julie Bowles, and I am presenting my microcosm project for general ecology. Today is October 20th, 2019. I undertook this assignment because I wanted to further my knowledge about microcosms. I had made a microcosm before, but had not incorporated any heterotrophs, and was curious to see how the system would be self-sustainable, as well as the interactions between the heterotrophs and autotrophs. Microcosms can be used in ecology as a heuristic model, either as inductive for prediction or deductive as an explanation. They can also compare an open or closed ecosystem, natural or synthetic, by size, etc. The limiting factor would be when attempting to compare or contrast different ecosystems. The microcosm's aquatic source was from a pond that receives a storm drain runoff. The banks of the pond have a significant amount of algae and rushes that run along its borders. The sediment around the pond is clay and sand, but challenging to get samples due to the extreme heat that's found in northern Texas from May to November. For my hypothesis, I hypothesize that the microorganisms in the water will thrive, but the plant life will not. I hypothesize that the heterotroph will not last longer than 4 weeks into the experiment. I predict this because I believe that microorganisms will be able to sustain themselves. However, the heterotrophs I used is free-floating algae, and I don't believe it will be able to survive or contribute to the ecosystem. To develop my microcosm, I selected a nearby water source, as you can see in the photo above. I used this water source because I thought it would have an adequate supply of water, heterotrophs, and autotrophs in a natural ecosystem. I used a 1,500-gram peanut jar, 3.5 centimeters of clay dirt, 2.5 centimeters of sand, 8 centimeters of water, and 3 centimeters of air in my microcosm. I selected a large sample of green algae as my heterotroph. I did attempt to visualize microorganisms and macroorganisms to include in the experiment, but I wasn't able to find any at first glance due to the murkiness of the water. The microcosm project ran for 7 weeks. It received full sunlight for the majority of the project during daylight. Only a few days of the project was there any rainfall or cloudy conditions in the area. The temperature was kept at 21 to 24 degrees Celsius. I left the microcosm on my windowsill in my kitchen, where it remained for the length of the experiment. In the initial stages of the experiment, the microcosm was cloudy and difficult to see anything distinguishable. As the sediment settled, it became much easier to see the autotrophs, mainly microorganisms floating in the water. They were very small, and I had to use a small magnifying glass to see them. The macroorganisms I saw were 3 small snails that were kind of hidden in the sediment. The heterotroph I selected, I believe, was too large for the microcosm, as it did impede the visibility of the majority of the microcosm. The sediment color was a deep brown, but the sodium carbonate did combine with the sand that created an additional layer to the sediment. The water began to become more evident, more clear over the 7 weeks the experiment ran. As you can see in these photos, the clarity of the microcosm became easier to see over time. However, the size of the autotroph did make it more challenging to see the entire microcosm easily. I did reject my hypothesis because the heterotrophs lasted the length of the experiment, whereas the macroorganisms perished after a few weeks and were floating in the top of the water. The microorganisms were still thriving, through the length of the experiment. In the experiment, the algae sample I used was rather large for the container and did make visibility a bit challenging at times. My observations did not support my hypothesis, but it did make it easy to reject it because the raw data proved my hypothesis null, as the algae still contained chlorophyll, that green color. It did not completely sink to the bottom, only hovered on the surface, similar to how it would in its natural environment. The 3 course concepts that were applicable in my experiment were the first concept that determines the limitation of how large a population can grow in an environment without exceeding its resources as carrying capacity. The second concept is competitive exclusion, when 2 or more species can't exist if they're competing for the same limited resources and maintain their current size of their population. Lastly, eutrophication, when there's an increase in the amount of nitrogen, plant nutrients, in an aquatic ecosystem, it naturally increases as resources are broken down, and excess nutrients can lead to hazardous conditions if not maintained, like blue algae blooms that kill local wildlife. The microcosm plant life I used reads a form of epiphyte that does not need to be rooted in order to use resources. I believe the rejection of my hypothesis feeds into all three concepts. First, the carrying capacity of this microcosm has exceeded by the size of the heterotroph, which had a detrimental effect on the microorganisms. The competitive exclusion forced the macro and microorganisms to compete for the same resources, and since the microorganisms were more substantial and would require more resources to sustain themselves, they perished. Lastly, eutrophication began to increase when the algae were able to use the calcium carbonate and sodium sulfate as additional resources for the algae to consume. And the size of the algae can also block sunlight and suffocate other plant life in its normal environment. If I were to perform this experiment again, I would like to test the effects on decreased plant life. As the ecosystem itself had a much larger water source and heterotrophs only on the outside of its perimeter, in the future I would ensure I select a sample that matches the size of the microcosm to ensure that it doesn't cause any margin of error in my results. The advantage of using microcosms that are relevant to general ecology is it can determine the effects of an experiment without causing irreversible damage to the entire ecosystem. The size of a microcosm can make it much easier and more cost-effective to study multiple experimental parameters. The most useful, innovative design is the effect of chemicals on the microcosm to determine the actual biological impact on the system. It can discover if there's an impending extinction vortex, if the ecosystem is suffering, for example, if there's an external source that's harming the entire ecosystem. In my experiment, I used a pond that is also fed through storm runoff, which opens up to sources that can have detrimental effects on the entire system. These are my references below. Thank you.